Yeah, the time is the time is 6 to. I will start it in 2 minutes till the students can join. I will wait for 2 more minutes and then I'll start the session. Okay, good evening all. My name is Srihari. I am the TA for the course of Advances in Welding and Joining Technologies for the NPTEL problem solving. The course instructor is Professor Sarup Bag and my name is Srihari. I hope my audio is audible and I am visible and my screen is visible properly. Okay, okay. Today is the sixth live session. Today we will be discussing on the fifth assignment, basically which is on micro nano welding. And today I will be discussing for first 10 questions will be from the last year's assignment and next 10 questions will be from this year's assignment. Initially few problems will be there, then there will be a theory questions. So first question is like I will wait for any replace. Okay, I'll read the question first. First question: dash laser micro welding technique is used to weld transparent polymers without the use of any absorbing materials. Without use of any absorbing materials, then as it is discussed in the class, the answer, and since it is directly straightforward, the answer is which is already discussed. 1B is the answer. Means twist laser micro welding technique is used for welding transfer without use of this. In shadows and all, uh, we need to have some interface for some interface some interface of absorbing material so that it can be used. But in twist, like with the twist, we can directly go with twist without any absorbing material. Let me take a pen. Yeah. First of all, average laser power at 100 watts is used for laser welding. The power density is 35 into 10 power 8 watt per meter square. Calculate the diameter of the laser spot. So P is equals to, so what they have given, power density. So this, let us consider this as PD. Power density is equals to power per unit area. Power per unit area. Power per unit area. Calculate the, now what they have asked is like calculate the diameter of the laser spot. Since we know that area is equals to pi d square by 4, we need to this d square we need to transfer here and power density will come here. So P by pi by 4, P by pi by 4 PD and square root will be there. So if we calculate, then if you substitute, we'll get the after substitute we'll get the answer. Here the units for power density is SI units, and also for laser is also watt, so it is also SI unit. So we no need to worry. We need to substitute. Once substituting, okay, let us check the answer. So as I explained, we need to take square root of this after interchanging PD and d square. So we'll get it as 1.9 to 10 power minus 4 meter. 1.9 to 10 power minus 4 meter. In the option, it's mostly they have given in a micrometer. So we need to convert it to micrometer. So it should be 10 power minus 6. So 10 power minus 6 means we need to multiply. This is straightforward only. 10 square into 10 power minus 2. So this 10 power minus 10 power minus 10 power minus 6. This 10 square into 1.9, 190. So you get 190, 10 power minus 6. 10 power 6 meter is equal to micrometer. So the solution for this is 2a. The solution is 2a. So if you guys have any doubt, please I think today's students are very less. Okay, I proceed further. In laser, an average. Okay, this question is done. Now, two steel plates with thickness of 1 mm, each will be spot welded at 4000 amperes. Assuming the effective resistance is 500 micro ohm and the current flow time is 0.4 seconds. 0.4 seconds. The heat generated in the process is basically it's directly heat generated I square R, RT. I square RT. I is given. R means SI unit of R is ohm, right? Micro ohm is given, so 500 10 power minus 6. Then T, 0.4 seconds. Then T is 0.4 seconds. So if you substitute, okay. So the yeah, for the sake of continuity, I will be starting. For this question, it's like straightforward. So without any observing material means only twist and other things and all, we need some transparent material, some observing material. So first one B is the answer, and for this is directly uh, uh, here they ask us to calculate the diameter of the laser spot. Here they have given power density and the power. So this form based on this formula, if you substitute, we'll get it as 190 micrometer. While converting, we need to be careful about the SI units, but ultimately we'll get it in meters. Then we need to convert into micrometer. I was discussing this problem like two steel plates with thickness of 1 mm each shall be spot welded at 4000 amps. So current given as 4000 amps I. Assuming the effective resistance 500 micro ohm. Ohm is this SI unit, so we need to convert micro ohm to ohm. So 500 10 power minus 6 resistance, and the current flow time is, so T is equal to 0.4 seconds. determine the heat generated in the process. So I square RT is the formula. So if you substitute, we'll get into 3200 joules. So for third one, D is the option. Any doubts, please post. Keep it in chat box. Okay. A diffusion bonding process is being carried out at 900 degrees Celsius, assuming the activation energy for so Q, this Q is 150 kilojoule mole, so 150 into 10 power 3, and the temperature is given as T is equals to 1173. The material constant D naught is given, and the universal gas constant as determine the value of diffusion coefficient. So diffusion coefficient formula we know is like D is equals to D naught e power minus Q by RT, right? So, oh, sorry, minus D is equals to D naught into e power minus Q by RT. Q is given and R is also given, so we need to substitute. Once we substitute, we'll end up with this 2.09 into 10 power minus 11. Uh, so option is C. I think. Yeah, C is the answer. Okay, I will proceed for next question. In the resistance micro welding, the applied voltage is 3.5 volts and the overall contact resistance per unit area, but heat is 1.5 10 power minus 1. What is the amount of heat generated? I think you guys are following. What now, the question they have asked is like, what is the amount of heat generated per unit area? So, uh, resistance is given in. So this is the formula, right? I square RT. Resistance is given as ohm centimeter square, and they ask us to calculate per unit area, heat generated per unit area. So, but per unit, what they are per unit area per unit time. So this T will go here. So ultimately we need to calculate H by T. So I square R we need to calculate. But here they have given us 3.5 volts. From the relation we know that V is equals to Ri. So V is equals to Ri. So we can replace V by like I by V square by R. So V square by R square into R. Uh, so R will get cancelled. Ultimately, we'll get V square by R. So once we substitute for voltage and corresponding resistance, we'll get the equation as 8.17 10 power minus 4 watt per centimeter square. One more thing. Uh, Here we are since in the question he has asked means it is asked to find the watt per centimeter square. So we are substituting directly this resistance to centimeter square only. We are not converting it to SI units. If they are suppose if it is asked to like calculate in watts per meter square something like that, then you would have converted. Since here they have asked directly about watt per centimeter square, so we are directly substituting. This also sir has discussed like many problems sir has discussed. In the pulse laser arc welding process, the pulse energy is 6 joule. Pulse on time is 4 milliseconds. Calculate the peak power and calculate the peak power and pulse time. So peak power and pulse off time of the system if the pulse frequency is 20 hertz. So pulse energy is given. So if you see in this figure, it shows this is the peak power and this is the pulse energy, and this is the pulse on time. And suppose if I consider this as a one cycle, uh, so from here to here, as it is mentioned, it is like peak pulse on and this is pulse off. So what they have asked is like they have given pulse energy. Fine, means the area they have given area of this rectangle. Once we know the terminologies, it's like some basically a kind of a geometric relation only. If you don't know anything about welding, also you can solve. If you know the geometric area, those things. So pulse energy is 6 joule, and pulse on time is 4 microseconds. So x-axis also they have given 4 microseconds. Where they asked us to calculate peak power. Basically, we need to calculate peak power in the sense this, right? So for a rectangle of a side A into L of side A comma B, if the area is A into B, right? So peak power into pulse duration, it is also called pulse width, is equals to pulse energy. The area is given by pulse energy. So uh, what happens, we know that it's a pulse. So we know that they have given 6 joule, and also time duration they have given as 4 into 10 power minus 3. So energy, the overall area is 6 joule and time is given as 4. So if we substitute directly the area formula, like power power into time, power into time is equals to pulse energy. I will write it as PE. This is basically this area formula. So all you need to know is the concept of this. If you know this graph, then rest of the things you don't need to remember anything for to solve these kind of problems. Just you need to know the terminologies itself. So now they have asked, like, okay, pulse energy is good. Yeah, B. Yeah, B is the answer. Yeah. For sake of clarity, I will be, so pulse energy they have given 6, and pulse on time is 4 milliseconds. 6 by 4 into 10 power minus 3. 6 by 4 into 10 power 6, so 150, 1500 watt. So once you calculate this, you can directly go for B, because all only 1500 watt is there. You don't need to calculate for other also. Okay, anyhow. Next question is like pulse of time. Pulse of time means actually this is the total cycle time. This is the on time, this is off time. They have given this, and in terms of frequency they have given over cycle time. So 1 by 20, if you do 1 by time, this is t, this is t. So t is equals to 1 by 20. So 1 by 20 means 0.05 seconds, minus what is this all on time, 4 milliseconds, right? So 1 by 20 minus 4, 1 by 20 minus 4, so half time is like 0.05 minus 0.004 is equals to uh, zero point 0.04. We'll get it as 0.046 seconds, and we need to convert into milliseconds. So into 10 power minus 3. So we get 46 milliseconds. Next question. Uh, Consider the following statements regarding the laser welding. Conduction mode welding is normally used for welding thin sheets, whereas keyhole mode is welding used for much thicker sheets. Obvious, right? Like this is basically we have sir would have been discussed this in at least 3-4 classes about the keyhole mode in the introduction class, and next week when explaining about the electron beam and laser beam. So it's discussed rigorously. So conduction mode is, yeah, this is true. Yeah, yeah, C is the correct answer. Basically, this is correct, right? Like conduction mode is normally used for thin sheets. Yeah, true, because the depth of penetration is less in conduction mode, and keyhole mode depth of penetration will be more. Uh, so it can be easily used for much thicker sections. That is true. So, and also vapor pressure generated, because like once during keyhole mode, the temperature generated will be more than the melting point, more than the melting point. Uh, so once the more than melting point, vapors will be generated. That will that because of the vapors, the vapor pressure will be created. So vapor pressure from the hot metal helps to keep the keyhole open. Yeah, that is true. During keyhole mode, once the so basically yeah, uh, once the laser comes, vapor will be generated because of the vapor pressure created, and keyhole will be there. So once the laser moves, that keyhole will be filled by the liquefied metal, and solidify happens. That is the process, right? So 7C is the answer. Consider consider the following statements regarding the resistance micro welding. Okay, resistance micro welding. Basically, in resistance micro welding, as I discussed, uh, we'll apply low pressure in resistance micro welding. That is the main catch there. So high contact resistance. So obviously, if I suppose if these are the two plates and the uh, pressure from the electrode, if I apply less pressure, then there will be some little gap inside. So obviously, if there is a gap, then there is no metal. Then there will be like contact resistance, right? If there is a gap uh, because of asperities. Obviously no plates will be exposed, so because of surface roughness or asperities there will be some gap and you are applying less pressure, the contact resistance will be more. uh, I don't get someone has okay. Okay, anyway we'll check it. Higher contact resistance is observed in the higher contact resistance is observed in resistance micro welding compared to large scale resistance welding. Yeah, that is true because we are applying less pressure, and the reason given is the electrode pressure is much lower in micro welding. Yeah. So both are is the correct reason. Yeah. So 8A is the answer. In this question, which of the following statements are correct regarding the ultrasonic bonding? So basically, this is ultrasonic bonding, and this is wet shape. One more type is also there. Uh, so we will be vibrating the sonotrode with the ultrasonic frequency. Because of that, the plates will be vibrating, and there will be and also some kind of clamping force. A little pressure is also applied. So in interface, because of the friction pressure, the bonding will be happening. So we'll check the options. uh, what they have given. High frequency vibrations with low pressure are used to cause the plastic from. Yeah, that is true. That is true. Someone has given the answer as D. Okay, let us check. They have asked incorrect. Small rise in temperature is observed. Yeah, because of the friction rate, temperature will be raised, and vibrations are responsible for removing the interfacial oxides and contaminants. Vibrations are responsible for removing the. Yeah, that is also true, right? uh, Physically we have oxidation contaminants in solid state welding and all. We need to remove that to get the in any joint in any welding we need to remove that. So while here vibration is used, the bonding force required is much higher than the thermocompression bonding. Yeah. First of all, that is true. So sorry, is less than the thermocompression welding, but here they have mentioned like much higher. So 9D is the answer. This is the incorrect statement. Basically, thermocompression bonding means thermocompression bonding generally it is used to weld wire or some kind of wire welding kind of thing. So if I am able to play this video, let us see. Actually, don't know. I wanted to show this video. Something error happened. Yeah, I think now video is visible. So because of this, the electrode will you can observe one more time. They will keep the wire and they will apply the pressure, and temperature will be more. Because of that, joint will be happening. So basically, compression force, and it is at a higher temperature. This basically is a principle kind of similar to diffusion bonding. Those things. Uh, so basically, we need to preheat. Then we need to apply compression. So we get that. So obviously, we need to apply more force, right? Let me obviously we need to apply more force, right? Because here friction is there. Because of the friction, it is vibrating at friction ultrasonic frequency. So because of the frequency, friction will be there. So clamping force required is less. But here there is no such things, friction and all. So only thing is like uh, uh, the temperature, so we need to apply more compressive force. Uh, so this statement is false. So 9D is the answer. So which of the following statements are correct regarding the adhesive bonding process? This is also like adhesive bonding. Basically, you guys know, right? For adhesive bonding, the bonding. It is basically the attractive forces between the adhesive and also the and adhesive and the component which you are about to join. Uh, so uh, what it is given, like the bonding relays and the attractive forces between the molecules or the surface of the adhesive and that of the surface to be joined. Yeah, that is given. Uh, Generally, larger the adhesive, there will be more surface area, so more more joining will be happening. So, which of the statements are correct regarding the bonding relation, the attraction force between the molecules at the surface of the one and that of the surface to be joined? Yeah, this is correct. This is correct. Then okay, no doubt. Okay. Smaller molecules better, but no, larger molecules should be there. And liquid adhesives wet that don't require any form of curing. No, first initially that liquid adhesive will wet the of surfaces to be joined, and it will raise it the temperature to 150 or generally 150 degrees Celsius. Then we'll cure it. So the curing temperature is generally in the range of 150 degrees. So this is 3 hours of false. So 10A is the answer. Match column A and column this from 11th question onwards. This year's assignment, assignment. So match column 5, column A with column B. So the question is like here they have given nano joining and categories of joining process. So diffusion bonding. Diffusion bonding. Okay. Diffusion bonding means you can directly go for solid state bonding, right? Diffusion bonding. Flip chip bonding. Actually, this is a soldering technique. Okay, if you don't know about flip chip technique, but in sir slides he has mentioned you need to look through it. Glass sealing means since glass is involved, you can go for possible. You can go for uh, laser welding, right? So fusion welding, C4, C4A2. This is there, C4A2. Adhesive sealing means obviously adhesive bonding, D3. So B1. B1 means flip chip bonding means soldering needs to be done for soldering is the mechanism used there. So 11, 4 is the option. Yeah. Uh, so match a column A different welding process and a column B working condition. Laser beam welding. Uh, so laser beam welding, electron beam welding, microplasma arc welding process, friction welding. So basically, in the options, heat generation by friction. So obviously, D2 is the answer. D2 is D for D. It is 2. Then microplasma arc welding process. Microplasma arc welding process. Uh, yeah, 3 is the answer. Microplasma arc welding process. The characteristics of microplasma arc welding is like stable arc at lower current. So C4. So C4 D2. This 2 is done. Then electron beam welding. Worked under obviously electron beam welding in required vacuum condition. That's why it's costly compared to laser and all, right? It's because one of the reason that it is costly. So electron beam welding B3. Then laser welding, obviously nut gas. Sometimes if sensitive materials are there, we can go for in a net gas ambient also you can do. So as you said, it's like 12. So materials that are susceptible to deformation or cracking can be joined by ultrasonic bonding. Okay. In ultrasonic bonding, interfacial oxides are displaced by using pressure to form a bond. Yeah, this is correct. Like we'll apply some pressure and we'll vibrate. And since it is a solid state welding, this is also correct. So both A and yeah, nothing B is the answer. Okay, we are running out. Okay. Which of the following statements are correct about microplasma arc welding process? Basically, you guys need to thoroughly need to know about the characteristics of the microplasma arc welding to answer this question. First of all, so a stable and concentrated arc can be achieved at a lower current. Yeah, this is true. And shorter weld times are possible. Yeah, the width of the heat affected zone is large. Okay. Basically, name itself microplasma welding, and obviously then heat affected zone is less, right? So this is wrong. This is wrong. And the transfer of arc occurs with the lesser frequency of noise. This is also because we are operating at lesser amperes, so compared to normal plasma welding, this will be like less only, right? So 14D, 14D is the answer. Uh, this is also all you guys need to know is like what is soldering, what is brazing. Okay. Which of the following statements are correct about the soldering or brazing? Brazing is considered to occur at a temperature greater than 450 degrees. Yeah, it's true. Soldering is generally used for joining wire in printed circuit boards. Yeah, just now I said flip chip bonding. Let me go to that slide. Where is that? Yeah, here B1, we classified it as B1, right? Like flip chip bonding. That's what. Soldering is generally used for joining wire in printed circuit boards. That's what flip chip bonding. And also soldering and bonding is used for joining material having high melting point. Uh, Actually, it's not the case, right? We'll go soldering or brazing whenever one of the metal is less than like a very low melting point. That's why the third is the wrong answer. Both similar and dissimilar metals can join. Obviously, we can join, right? Because we are using third filler material, and joining is happening without like not like fusion welding and all. So basically, wetting action happens, capillary action and wetting action. Because of that, deposition like joining is happening. Uh, so except yeah, no, 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 no. C is the answer. C is the answer because this third statement is false. That's why C is the answer. Which of the following process parameter of ultra pulse laser welding is used to determine the time in which energy is stored in electrons? Basically, this ultra short pulse means within small duration the laser will be on and then laser will be off. So because of that, there will be a relaxation time. Some lag will be there, right? To conduct the heat from the laser to the heat from the electrons to the base plate. So there will be a lag. Yeah, relaxation time is the answer. So basically, what is the question? Which of the following process parameter used to determine the time in which energy is stored in electrons? Obviously, there will be delay in lag. So what is the question? Please explain transfer arc efficiency. Okay, sorry. Transfer arc process, right? Efficiency of what is charts? Let me check the chart box. Basically, transferred arc and non-transferred arc will come in plasma, right? Mm, basically, we use like a plasma gas should be supplied that the gas with electrode, and also there will be another shielding gas that is called non-transferred arc. Here will in non like transfer documents is it's like standard process where there will be a electrode and one we can use two different shielding gases or same shielding gases. So with one will be like used there will be two plasma shielding gas and some normal like shielding gas we call the so with the plasma shielding gas plasma thing with the help of that like arc will be generated and there will be externally there will be shielding gas is there. This is the normal thing that is the non-transferred arc. Uh, so in what you asked is the transferred arc, right? Suppose if I want to add some kind of kind of surface on the workpiece, then I can supply the powder along with the shielding gas. That is called transferred arc welding process. That's it. That arc initiation and everything will be same. If we want to add some material, then we'll supply the powder coaxially along with the plasma welding to uh, basically to deposit the surface on the uh, given material. That's it, like that. So where were we? Okay, which of the I hope which of the following process parameter of the ultra short pulse laser welding is used to determine the time in which energy is stored in the electrons? Yeah, lag will be there. That lag itself will tell that the till that lag that it won't be conducted to the base plate. After that time only it will be conducted. So it will be storage also. Relaxation time is the answer. Relaxation lag, the delay in that conduction. So match different process parameters of pulse current plasma arc welding with the different process parameters. Okay, first of all, uh, pulse repetition rate means number of pulses present in a given second. Basically, it's a frequency, pulse repetition rate. So A4 number of flash pumps pulses per second means basically this from I'll take it from 1 second. So this is one cycle till here. So peak current plus base current. Uh, so this is one pulse and number of pulses repeated per second. So A4 is the correct thing. Then pulse shaping, basically whether it is rectangle or even sometimes you can use triangle and some other things. Uh, so basically that so we can use it for enhancing the welding quality in the sense whether suppose if I use triangle, we may get the different kind of bead. We will get the different kind of bead compared to the rectangular and triangular if we compare. So basically, it is used for enhancing the weld quality. You were telling me here, right? Let us check. Uh, pulse width. Pulse width means this is the width, right? Duration of which pulse is applied. At last, I think in some questions, some third or fourth, I don't know exactly. There also I have discussed. So C2, B, B3, A4. Pulse energy depicts the energy contained in the pulse. Yeah, that this cross-sectional area. D1. So A 17A, as you say, 17A is the answer. So match column A with column B. Joining. Here, some if you go through the slides, like titanium, it's not like so. Titanium is given by resistance welding. It's not like only titanium is welded by only resistance welding. Based on the matching, we need to select. For titanium, it's like resistance welding, and also we can go for laser ultrasonic. But if I go for what are the other things? B3. Silicons, obviously, it's the adhesive bonding. It's mentioned in the first slide only. These are the things we need to know. Basically, you need to know the principle on what is the like material and whether it is a whether it is 18 1. No, let us check. Okay. B is adhesive bonding. Yeah. Lead-free solders and polyurethane. Uh, Polyurethane, laser and adhesive. See, polyurethane it has given us laser and adhesive, and we are matching this silicon with adhesive. So polyurethane will take laser. Yeah, lead-free solders, ultrasonic C2. Yeah, yeah, one is the answer. I was confused with the second option, but one second, one second. Yeah, yeah. Even now I am checking. 18 1 is the answer. But somehow in key it is mentioned like 3. A4. No, silicon is for adhesive. B3. So B3 means 1 or 4. Then C, lead free solders means yeah, 1 is the answer. Maybe in the key is mistakenly written or something. Some typo has happened, I think. So 18 1 is the answer. Then which of the following phases belongs to the laser micro welding process? Uh, okay, droplet creation, droplet detachment, droplet landing, droplet solidification. Yeah, all three. Basically, what happens? Droplet will be created in this duration. Droplet will be created, and it will be moved to the position. This is where our target, we are supposed to weld. Once it is target is set, and again we'll raise the power, where the pulse will give the pulse. So droplet will be detached. Once the droplet is done, there will be a flight for a droplet. Once the flight is done, it will fall in a particular region. After that, solidification happens. That is the sequence. So here I think flight is not mentioned anyhow. So 19D is the answer. Which of the following statement is incorrect about electron beam welding? First of all, this is wrong, right? It works under normal ambient mode. Uh, Beam power is not suitable for welding of microscopic. Yeah, it is true. So that's why we need to modify it if we want to use it for micro welding. I think some researchers have done that also. Even sir has discussed in the class. By modifying scanning electron microscope is suitable for yeah, yeah, 21 is the answer. I think okay. Let us open. Last time while discussion, I said that welding sequence is very important for changing the distortion or for resistance, right? Yeah. Let me show the some. I think this paper is visible for you guys. In this research paper, basically it's for additive manufacturing, but you can, it's like nothing but you can directly correlate to the even for this thing also, like welding also. So basically after welding or deposition, there will be a roller, we roll it so that tensile residuals is generated in the component as I explained in the last class. Again, I think you guys remember it, in free bar arrangement there will be a, initially during heating compressive stresses will be generated. Once it is cooling, the tensile stresses will be generated in the center bar, and the adjacent bars there will be a compressive stresses. Fine. After that, so if you want to correlate to that to the welding, so welding, so wherever welding happening, that region and nearby region you can correlate to the center bar. So there will be tensile stresses, and adjacent away from this will be compressive stresses, which needs to be avoided. So for that there will be like as I discussed, there will be short pinning, and also one more rolling. This is the rolling and hammering, and also weld sequence also important. For distortion, I think weld sequence is important. I don't remember exactly what. Mainly for restorations, then because of that, even distortion will be reduced. So for rolling, how what happens is like once you apply compressive forces on the component, the residual stresses will be. See, you can see here, right? This is the additively manufactured component. It will be distorted because of the generated residual stress and all. Generally, we'll clamp it. Generally, we'll clamp the specimen and we'll deposit weld or something. A resistance will be generated. Once we unclamp it, stress redistribution will take place, and so because of that, distortion happens. That is the main this thing. So for to avoid that, initially we wanted to remove the residual stress. So you can see here in this figure, this is the contour maps of residual stresses. This is the as deposited component. This is the cross section of the as deposited component. You can see here, right? There will be a lot of residual stresses at the center, away from the at the center. At the intersection, there is a lot of residual stresses developed with the additively manufactured component. This is even valid to the welding also. So what researchers has done is like they applied the rolling, like after each layer deposition or after welding, will roll with the help of some load, because of the compressive stresses and the tensile stresses cancels. So you can see in the B and C, there is a reduction of tensile stresses, right? Tensile stresses. Because of the indirectly distortion also will be reduced. This was I wanted to show. And one more thing I wanted to show is this is also another paper. So basically, and also last class I was explaining about computational welding, right? Even thermomechanical welding, where we can, with the help of thermo modeling, we use the temperature input to the mechanical modeling to predict the distortions. And with the help of that also, with the help of that modeling, we can even basically I wanted to show a few applications even in additive manufacturing or in welding, so that it will motivate for you guys in this study and all. So basically, this is the plate and this is the deposition or welding, anything you can consider, and these are the clamps. So the point is like where should I clamp and how many clamps should I use? So it's not like anyhow I have experimental technique like something like XRD or radiography or something. So XRD or contour method. With that I can directly measure the vestibular cells. So what I can do is like I will clamp for 8 clamps and I will deposit a component, or I will. I think I lost internet. One second.
Check the speed before operating. Huh?
Sorry, sorry, I think there was an internet issue. So, what I was telling, like during additive manufacturing or during welding, first, so the thermomechanical modeling, why it is important, or distortion in that welding sequence and all is like with the help of the modeling itself, you can without doing any experiments, without using like without spending some like without spending any material or anything, with the help of numerical simulations, you can get the result and you can use the optimum result so that we can save the savings of material, even money, time, everything. So in this thing, so like so how many clamps I need to use, or even sometimes even what is the welding sequence and all. And those are all is the thermomechanically simulated, and based on the results, uh, we'll select the proper proper technique which should be used for means which like what clamping kind of thing. Here in this case, what kind of clampings is the final thing based on simulations, where you can observe with the four clamps here that this is how the resources is distributed. Mm, and in that this kind of arrangement of four clamps, this is how the distribution, and similarly for other cases. Uh, so this is how it's very useful. So I think today I will